Here we have a question. In this question, we have to determine the maximum deflection of the simple supported beam. As you can see, there's a force P acting in downward direction, which is equal to 600 lb. So here, the modulus of elasticity is given to us of the given wood, that is 1.5 into 10 to the power 3 ksi. So here, in order to find the maximum deflection, we must know the moment function. For that, first of all, we'll find the reaction support force at point A and at point B. Let's suppose at point A, the force is acting in upward direction, which is Ra, and the force which is acting in horizontal direction, because it's pin supported at point A, so it will have two reaction supports. Let's suppose that is mm, Fa. And at point B, let's suppose there's an upward force which is supportive force, which is Rp, because it's a roller support at point B. So we can say that there's only one force which is acting in upward direction at point B. So here, as we apply the condition of equilibrium, we can find the value of force Ra and Rb. As we take moment about point A equal to 0, and as we equate all the vertical forces equal to 0, means the summation of vertical forces equal to 0, we can find the value of Ra and Rb. Now, as we can see, there's only one force acting in horizontal direction. So we can say that the value of Fa will be equal to 0. And after that, as we find the reaction support forces, we can apply the moment function for this portion from point A to P. It would be different, and for the portion P to B, it would be different. After that, we will equate the moment function mx, which will be equal to our elastic curve and slope equation, that is E into I multiplied by d square V divided by dx square, where E is modulus of elasticity, I is moment of inertia of the given beam. So now let's move forward. Let's see what's given. As we can see here, the modulus of elasticity is given to us, and the distance of point load P from point A is 8 feet, while the value of load is 600 lb. And after that, we are given the width of the beam, which is 3 inches, and we are given the depth of the beam, which is 6 inches, and the length of beam is given to us, which is 12 feet. So with this data, we can find the moment of inertia of this given beam, means the given wooden beam. Now let's apply the condition of equilibrium in vertical direction. So as we add the reactive support force at point A plus reactive support force at point B minus 600 is equal to 0, because we are considering the forces in upward direction as positive, while we are considering the forces in downward direction as negative. And also we'll consider the counterclockwise moment as positive, while we will consider clockwise moment as negative. So from here we can write Ra plus Rb equal to 600. We'll name it as equation number 1. Now let's move forward and take the moment about point A equal to 0. Moment due to this supportive force of 400 lb, which is acting in upward direction, which is the value of Rb, and the value of, and the moment due to this force 600 lb, which is acting in clockwise direction. So from here, as we add Rb into 12, because this distance is total 8 plus 4, which is 12 feet, minus 600 into 8 equal to 0. So from here we can write the value of Rb, that comes out to be 400 lb. Now as we substitute the value of Rb as 400 lb in equation number 1, we can find the value of Ra, that comes out to be 200 lb. So as we discussed earlier, the moment function for this portion from point A to P will be different, and from point P to B it will be different. So as we can see, let's go at a distance x1 from the point A. So here we can write the moment due to this supportive force of 200 lb, that would be written as 200 into x1. So from here we can write the moment function mx1, that is 200 x1 lb feet. And same, we can write the moment function x2, that would be 400 into x2 lb feet, if we are at a distance of x2 from this side of 400 lb. Now we'll equate this with the elastic curve and slope. So here, as we equate this moment function for this portion from point A to P with the elastic curve, we can find EI into d square v1 divided by dx1 square, which will be equal to 200 x1. Now, as we integrate on both the sides with dx, we can find that it comes out to be EI multiplied by dv1 divided by dx1, that is equal to 200 x1 square divided by 2 plus c1. So from here we can write it as 100 x1 square plus c1. Now let's move forward and let's integrate one more time on both the side with dx. So from here we can write EIV1 is equal to 33.33 x1 cube plus c1 x1 plus c2. That is the equation number 5. Now let's move to the portion from P to B. Here, as we equate the moment function with the elastic curve slope diagram, elastic curve slope equation. So from here we can write it as EI into d square v2 divided by dx2 square, which will be equal to 400 multiplied by x2. We'll name it as equation number 6. Now as we integrate, we can find this equation as we integrate it for one time with dx. Now as we integrate it one more time, we can find this equation number 8. Now as we know, according to the boundary conditions, slope at this point is going to be 0, slope at this point is going to be 0. Here the value of x1 is equal to 0, and here the value of x2 is equal to 0. So from here we can find the value of c2, that comes out to be equal to 0, as we substitute the value of x1 in equation number 5. So the value of c2 is equal to 0. Now let's substitute the value of x2 equal to 0 in equation number 8. So from here we can find the value of c4, that is also equal to 0. Now let's move forward. As we know, at this portion the curve would be same due to the continuity in the wooden beam. So from here we can write, at this portion the slope is going to be same. So from here we can write dv1 divided by dx1 is equal to minus of dv2 divided by dx2. So here, as we substitute these values of dv1 divided by dx1 and dv2 divided by dx2, we can find an equation of c1 plus c3, that is equal to minus of 200 into x2 square minus of 100 x1 square. Now let's substitute the value of x1 is equal to 8 feet and the value of x2, that is equal to 4 feet in equation number 9. From here we can find a relation between c3 and c1, that is c3 equal to minus 9600 minus c1. Now let's consider x1 is equal to 8 feet and x2 is equal to 4 feet, and let's apply the continuity condition. Here the slope is going to be same, so from here we can write v1 is equal to v2. So as we know, the value of c2 and c4 are 0, and there's a relation between c1 and c3. So from here, as we substitute these values, we can find the value of c1, that comes out to be minus of 51,198.08 divided by 12. The value of c1 comes out to be minus of 4266.51 lb feet square. This is the value of c1. Now let's substitute this value of C1 in equation number 10 and find the value of C3 that comes out to be minus of 5333.49 lb feet square. Now, as we know the value of C1, C2 and C3, let's substitute this value of C1 in, in the elastic curve of V1. So from here we can write the value of V1 as 1 divided by EI into 33.33 into x1 square minus 4266.51 multiplied by x1. So as we substitute the value, we can find the value of V1 and same we can find the value of V2. Now, as we know the value of E, we are going to find the value of moment of inertia that can be written as BD cube divided by 12. Here B is the width and D is the depth of the given wooden beam. So from here we can write the moment of inertia that comes out to be 54 inches to the power 4. So here, as we know, we are going to find the maximum deflection. For that, we will write Vmax equal to 33.33 into 6.532 whole cube. So as we substitute these values, we can find the maximum deflection at this point that comes out to be minus 0.396 inches. So from here, we can say that the maximum deflection of the simple supported beam is equal to minus of 0.396 inches. This deflection is negative because there's deflection in downward direction. Thank you.